When we talk about finding alien worlds, it is easy to picture a pristine, high-resolution snapshot of a distant, cloud-swirled planet. But the James Webb Space Telescope cannot take a crisp photograph of an exoplanet's surface. The physical reality is that these worlds are hundreds of light-years away, and they are completely drowned out by the blinding glare of their host stars. Trying to capture the planet visually is like trying to spot a firefly crawling on a searchlight from 50 miles away. Fortunately, we do not actually need to see the surface. We just need to catch the starlight that grazes the very outer edges of the planet. To understand the true nature of an alien world, we have to look past photography entirely and rely on advanced chemistry. The process begins with a planetary transit. This happens when a planet's orbit carries it directly between its host star and our line of sight. Starlight filters through the thin ring of the planet's atmosphere before continuing toward Earth. As it pushes through the alien air, specific gases act like a filter. Different molecules absorb distinct colors of light, while letting the rest pass through untouched. To catch those filtered light waves across trillions of miles of empty space, scientists built an incredibly sensitive array of gold-coated mirrors. Once gathered, instruments like the near-infrared spectrograph act as advanced prisms, taking the incoming light and splitting it apart into its individual, readable wavelengths. The light that finally hits the detectors carries a precise, invisible signature of the exact gases it touched along the way. This line graph shows the transmission spectrum of a distant planet across infrared wavelengths. Scientists search for specific dips where starlight is simply missing. These are chemical fingerprints. Seeing identical gaps for molecules like carbon dioxide proves those gases exist light years away. This chart compares the atmospheric chemical signatures of Earth, Venus, and Mars. Even though they share the same solar system, each planet's chemical makeup leaves a vastly different pattern of dips and peaks. This method of reading missing light is called transmission spectroscopy, and it is the definitive tool we have for mapping invisible gases across the galaxy. A planet's true identity is written in the specific pieces of light its atmosphere steals away. When people hear that we have detected water, methane, or carbon dioxide on an exoplanet, the immediate reaction is to assume we have found alien life. The reality of astrophysics requires much more skepticism. Completely dead, non-biological processes can flood an atmosphere with the exact same chemical signatures. Intense geological venting is a major culprit. Massive volcanic eruptions and shifting magma continuously pump tons of carbon dioxide and sulfur into the air, creating a chemical profile that mimics a breathing biosphere. Even smaller-scale geothermal processes can release methane and water vapor, perfectly matching the biological outputs we expect from living organisms. Because of these false positives, astrobiologists operate under a strict rule. The presence of life must always be treated as the hypothesis of last resort. Detecting the basic ingredients for life is just the starting line in a rigorous scientific battle to rule out dead geology. To beat the false positive problem, scientists cannot rely on a single missing wavelength of light. They have to read the entire spectral band holistically, looking for specific combinations of molecules that shouldn't exist together without life actively maintaining them. They also have to account for a massive range of contextual variables. They run models to predict global cloud coverage, estimate the temperature at the surface, and calculate exactly how much aggressive ultraviolet radiation is blasting the planet from its host star. Taking all of that raw data and turning it into a clear picture requires an immense amount of human and computational effort, with teams of researchers verifying models and debating conclusions for months before a consensus is reached. The James Webb Space Telescope provides the rigorous chemical truth of the universe. It brings us closer to the definitive proof of life through the systematic elimination of every other possibility.